Who was here last year? A few people. Okay, all right. So last year we had an interesting presentation from Stephen Temple, and he kind of challenged us with the kind of regulatory framework of radio and where it was heading, and he was involved in drafting the original GSM MOU way back in the 1980s, so he's quite an interesting guy. A lot of perspective, and he was looking at how the regulation of radio had changed over the years and was questioning whether today's regulatory framework, the one that's kind of brought us 3G, is going to be the one which is going to keep the industry moving forwards. So what I thought I would do in this presentation is sort of follow on from Stephen's question last year and propose a couple of options that might be interesting to consider. These are what you would call on the radical end of the spectrum, if you pardon the use of the word spectrum there. But I think it'd be useful just to get people thinking about some of the practicalities that are facing the industry over the next while. For those of you that don't know my background, I work with Agilent Technologies. I've been with them about 27 years, and I work primarily in radio standardization, which is in 3GPP. I used to work with ETSI. So I've been involved in radio standards now for over 20 years, and seen several generations, GSM, UMTS, now LTE, LTE-Advanced. And it's interesting just to try and draw some kind of conclusions out of that. So clearly, we've seen huge change in radio over the last 30 years. And it started off extremely small, and now, of course, it's very, very big, with GSM being the biggest adopted technology in the world. So, but what's the future looking like, really, is the big issue. So if we look at what's happened with radio formats in the last 20-odd years, it's a pretty busy picture. And I can use this slide for a variety of reasons, but the one that I will emphasize today is the fact that in the last 20 or so years, only 2 of these technologies have actually effectively been obsoleted. IS-136 in the US was switched off a year or 2 back. PDC in Japan will be switched off, I believe, in 2012. Everything else is still on the table. So anybody trying to address a worldwide market has to somehow make choices or try and do a bit of everything, which is very, very difficult. So the environment we're working in is a multi-format environment, and that creates challenges in its own right. But it's not just the formats. The other area where we've got a lot of challenges happening is in the area of frequency bands, and I've just done the latest update on this table. Every quarter, the Standards Committee adds 1 or 2 more lines to this list. Currently, we have band number 25 here has been added. There's a huge number of different bands in which we can operate radios. And there's a lot of overlap in these bands, which doesn't necessarily make the problem any easier. The reason there's overlap is because often there are problems with parts of the bands that you'd rather not want to go into, so you create sub-bands or whatever. It's related to coexistence issues and sometimes design issues with the terminals themselves. And you can see, looking at this list, that the width of the bands varies dramatically, all the way from, we've got some pretty wide ones up in the kind of 75 meg range there. The duplex spacing, the gap between the downlink and the uplink, varies dramatically from, we've got one up here at 400 megahertz, and we've got other ones that are down in the kind of, 15, I think we've got some very, very small ones. So there's large differences there, and also the gap between the uplink and the downlink, which is another variable. It drops as low as, I believe, 12 megahertz in some cases. And that, from a radio point of view, is a very hard thing to deal with, because you have to filter off your transmitter from your receiver with the duplex filter. So for instance, band 8 here is a big challenge to design in because of that problem. So the bands are just, there's more and more of them. People are hoovering up all the bits of spectrum that they didn't previously use in the earlier generations, when there was some obvious spectrum that could be used across the world. Obviously, we have the TDD bands as well. There aren't as many of those, but there are still quite a few. And it doesn't stop there. These are the ongoing discussions in the radio committee. There are 3 more bands that are definitely about to hit the streets. They are not quite there yet, but they might be in a few months. And then there's even more that have been identified by the ITU. So we have a very complex frequency situation. And one of the consequences of that is that in order to meet the requirements that the ITU have laid down for 4th generation, which is to reach potentially gigabit per second data rates, is you have to get more spectrum simultaneously applied in the radio. And the only way you can do that, if you have spectrum that looks like what I've just shown you, is you have to aggregate the spectrum. You have to simultaneously use more than one piece of the spectrum at one time. And within LTE, LTE-Advanced, the potential to aggregate up to 5 carriers has been specified. So this is the way in which the ITU have realized there isn't a large chunk of spectrum where you can just get 100 megahertz all in once. So they've realized that, they've allowed for it, and the LTE Advanced standard has responded by defining this concept of carrier aggregation. In addition to that, there are also further work going on in the area of enhanced transmission with multiple antennas. And we've moved in the original Release 8 standard from 4 antennas in the downlink to 8. And critically in the uplink, moving from 1 antenna, in other words SISO, to potentially 4 antennas in the uplink, so 2 or 4. That's a bigger change to the ecosystem than the base station end. Going from 4 to 8 is less significant than going from 1 to 2 on the mobile, because you double the number of radios in the mobile, in the transmitter. So there's also other issues. Even within one of these approaching 40 bands now, there are issues in terms of how to deal with the actual deployment of particular operator requirements. And there is ongoing amalgamation between carriers, and that's causing, even within a band, one operator to want to use simultaneous parts of the same band because they got some spectrum from one, from a legacy operator, and then some of their own, and they want to be able to operate it together to get more performance. So that's creating some challenges, and also there are difficult bands, and this is becoming more and more apparent in the radio committee. A number of the newer bands that are coming along are problematic from a coexistence point of view, and also in terms of the number of operators that may own a particular band. It might be quite small, and so this creates problems in terms of scale. It's starting to worry me that we're getting lawyers turning up to the standards committee. That's the FCC show up regularly now, and we've had some difficult discussions on some bands where an operator's gone out and bought the spectrum and assumed that it was okay to use. Then they take a closer look and discover, okay, maybe not. And there's some big issues right now in the US with interference between, or potential interference between terrestrial satellite use and GPS is a major one that's being discussed at the moment. And there are a lot of other combinations of bands that are problematic. And I don't follow these arguments closely, but you can really see how the operators who have gone out and bought spectrum in good faith have bumped up against the fact that maybe the standards committees weren't fully aware of the issues or weren't responsible in the case of GPS for the protection of another band, and the FCC may have some role to play in what's happened. So it's getting very, very difficult with these bands. To give you an example of how ugly things might look, even in one band, this is an example that came from T-Mobile USA that was just presented a couple of weeks ago in the standards committee. This is the AWS band, which I think is 1700 down, 2 gig up, I forget, something like that. This is their justification for why we need to standardize 4-carrier non-contiguous HSDPA in one band. So if you figure out which bits they own and which combinations of blocks they own or want to operate, you get all these combinations. And each one of these would have some implication on the radio design in terms of the filtering. And this is one operator in one band in the US, and I've got another one from Orange in Europe, and it just goes on and on. So this is what's happening. We don't have the ability to do this nice deployment of some nice wide fat bit of spectrum. There are very few places in the world you can do that. Then the US 700 megahertz band plan. I put the inverted commas on after I first wrote the slide. And you've got to say this is a lot of issues. It's fragmented in terms of the size of each of the blocks, very, very small. There's lots of coexistence issues here. Band 13 that's being used for LTE is next to public safety. Band 12, the bottom channel of band 12 is effectively a guard band between that band and another band. You know, it's that hard to use. And you look at this and you think, you know, what were they thinking? So you can't be serious. I mean, who would take a band of that size, which isn't big, it's about 100 megahertz, and break it up that way? Now, some of it's historical, but some of it was quite deliberate. They wanted to create competition in the market, and they certainly did that. But at the same time, they created a bunch of spectrum that, you know, 10 years ago might have been considered useful. But in today's world, where you're wanting to get 20, 40 megahertz of clear spectrum, you can't do it here. The 10 megahertz that in band 13 that Verizon has is compromised by public safety. They can't use all of it fully. They have to pull the control channels in order that the spurs created don't fall into the public safety band. And that then limits the size of the uplink they can use for the data. So they're limited, and also in power, they can't operate at full power at the cell edge. So these are not optimal pieces of spectrum by any means. And the scale also is a problem. There are operators that own certain parts of the spectrum that are frankly not going to have much coverage in terms of getting devices out of manufacturers. So that's another big challenge. So even though they've got the spectrum, they might not have the products to actually deploy in that spectrum. So why does it matter? Well, I've explained some of the reasons why it matters that all this fragmentation is going on. If we are trying to solve this problem with carrier aggregation in the mobile, it's non-trivial. That's definitely true. I mean, radio for 100 years has been based on the concept of a downlink frequency and an uplink frequency, or in the case of broadcast, obviously downlink only, but in the case of two-way radio, it's fundamentally been based on two separate frequencies, protected with a duplex filter. We understand that technology. We've been doing it for a long time, and it works. And as soon as you put a second carrier in there, especially on the mobile end, you enter a whole new area of design challenge in terms of intermod performance, self-blocking, all the rest of it. And then if you add a third, fourth, fifth, of course it gets even more difficult. So the way we've kind of got to here because I think some people took a sort of spreadsheet approach to the problem. You know, people in the sort of baseband world or in the regulatory world where you just see this jigsaw and think, oh, well, we'll just do a bit of that, a bit of this. It doesn't work like that in radio. When you have to actually design a product for a specific combination of bands, you have to go out and design that amplifier, that set of filters, just for that one application. And you no longer have a general purpose product which can just do anything. And there are performance limitations by going down this multi-carrier route. Because every time you have to put in another carrier, you've got another set of filters to design. They all create loss. So your maximum power goes down and your receive sensitivity goes up. So your performance in building, for instance, will degrade by a certain amount. And every time you add in more, it gets more complicated. And there are many ways of designing for this situation, and there aren't any agreements on what the baseband, on what the base architecture is. So it's very hard to even agree what the requirements are, because you can implement things in different ways. Like a 20 megahertz channel could be done with two 10 meg radios aggregated, or one 20 meg, and that has implications on the design of the device and the specifications and all the rest of it. And of course, if you have more radios in there, you're going to have a higher battery drain. The performance of the product is going to be not so good there. and then the cost implications of all these bands in the one device. Here's the reason why we don't do multi-format cars, because people basically know there's only so much you can stick in a car. Today, maybe you can get hybrid cars with a petrol engine and a very expensive heavy battery. And that's kind of about, or maybe with a petrol engine and an LPG tank. But you compromise. You lose space in the boot because you've got to put an extra petrol tank in or a huge battery. So in the motoring industry, pretty much, if you want an efficient car, you go single format and you keep it simple. In radio, we seem to be going the other direction right now. We're going for multi-format, multi-band. And that is going to have an impact on the cost, the complexity of the devices that are actually being developed. However, if you sort of stand back and say, well, what's the industry doing? And at the moment, pretty much the operators are asking for everything, because that's the easiest answer to start with. Just say, well, what can you do? And so we've got a number of operators who are challenging the vendor community with, can you give me a 13-band mobile with MIMO in a dongle? And that debate's going on, and I think there's a lot of optimism out there, on some fronts as to how much of that can be solved. But at the end of the day, choices will have to be made, and it's not practical to think that you can design a device that will do everything, and it's not yet clear where's the sweet spot, for what we want to do. So certainly on paper, with SDR, anything is possible. And we've heard some really interesting material just in the last presentation there from Alcatel-Lucent on what's possible in the base station. And certainly the multi-standard radio project that's going on right now in Release 9 has been very successful. And now I think it's reasonable to assume that base stations are capable of supporting multiple formats. The multiple band option is more challenging, but it's certainly within the cost constraints of a base station, which are not as tight as a mobile, and the power constraints are not as tight as a mobile, and the size is not as tight as a mobile. You've got freedom there to actually go and develop some of these multi-format designs. And indeed, as a test equipment company, Agilent's been designing multi-standard base stations for probably certainly 15 years. And that's normal because we have the margins in which to be able to do a broadband design, a 3 gigahertz wide power amplifier. But you don't do that at high powers. You don't create a 3 gigahertz wide 40 watt power amplifier. It would be obscenely expensive and power hungry. But you do have more flexibility in the base station than you have in the mobile. But the big problems with the mobile are primarily at the radio front end. It's the antennas and it's the power amplifiers. And unfortunately, those are still very much hardware-dominated things. They are not software-defined. There is work going on things like tunable filters, but we're a long way off expecting that you can just create one antenna and somehow tune it in order to get the optimal performance. And the multiplex filter design I've already mentioned, you can't violate the laws of physics. And some of the proposals I hear in the standards committee do require some quite amazing filter performance, which in reality is unlikely to be deliverable in a sort of normal production environment where you have to deal with tolerances and etc. So the problem we have is that we take multiband, you throw in carrier aggregation, you throw in MIMO, and you've got an antenna nightmare to deal with because of the numbers of antennas and the ways in which they have to be optimized for different frequency bands. So it's very, very challenging. So if we kind of step back and think, well, what did it look like over the range of time? Well, we started off with a brick, single antenna, analog system, very successful. Then we got the GSM era, and that's the Nokia 2110, which was one of the who used to have one of those? One, two, ooh, I'd say half the room. Very good. And then, of course, we got the smartphone. And my worry is that 4G is going to look like that, the hedgehog. If we went down the path that people are going down right now, it's not sustainable. And no hedgehog was harmed in the taking of this photograph. So here's the first alternative to how to solve this problem. Half duplex FDD. Now, how many of you are familiar with half duplex FDD? Ah. In that case, I'll jump to the next slide and show you what it looks like. So here's full duplex FDD. So this is what we've known for 100 years, whatever. Over time, we transmit on the downlink frequency, we transmit on the uplink frequency, and we do it simultaneously. And they're on different frequencies. And we have a duplex filter that separates the two. So it's what we know. More recently, we have TDD technology coming in. So we now only have a single frequency. And you time switch between downlink and uplink. And you have some flexibility in the relationship between those two, which gives you some load balancing. Although, to be honest, in any real network, it pretty much has to be 50-50 because you can't have different loads in different cells because then they interfere with each other in the overlap areas. But that's basically what's happening, and TDD is very much in the ascendancy. It had a kind of minimalist effect in 3G, but certainly with LTE, TDD is fundamental to the radio standards. There are no longer two sets of standards. There's one standard which has an FDD and a TDD option. And there's a TDD spectrum out there. It's not as much as FDD, but it's certainly not to be ignored. So that's TDD. Half duplex FDD is basically TDD operating on two different frequencies, but with the same capacity. The advantage of this is you do not need the duplex filter, which is what causes a lot of the problems in multi-carrier designs. So that's what it looks like. And let's have a look now at why would you want to do that? Well, basically it's an easier thing to design. Switching between two frequencies in time there's less hardware involved. And the standards, the 3GPP standards actually support this option as a way of working. Now, it does have some implications, and those are, the pros basically are simpler design, the devices will be lower cost, there'll be higher performance in terms of the radio because you won't have the multiplexer filter loss issues. And although you're only operating half the time in any one direction, the network as such is not impacted in terms of its capacity because you basically are scheduling users at different times. So when one device is receiving, another one can be transmitting because the issues, the coexistence issues are primarily in the phone themselves. But the cons are your data rates obviously are limited to what can be achieved with TDD systems. Now, nobody's complaining about TDD. It's just a different paradigm. You only have half the resource. In a 20 meg channel, you have half of it. 50% of the time you're transmitting, 50% you're receiving. So in theory, it's half the potential of an FDD channel. But nobody seems to be worried about that. You just accept that's the way TDD works. And half duplex FDD has the same performance. It's just that you're using two frequencies when you're doing it. And I expect that the latency aspects will slightly increase, but similar to what you get with TDD. So this is the concept of half duplex FDD, and it means that if you wanted to create a multi-carrier design, you're much more able to do it in this environment because you don't have to create this exponentially more complex set of duplex filters. You can do it much more simply by switching filters in and out as and when required. So this is something that's has been looked at before, but it's not something that I think is getting discussed as an option yet. And it's interesting that not many people here had heard about it as an option. But I think it's something that needs to be discussed more. Is this something that can free people up, free operators up to make better use of their spectrum, while not creating impossible demands on the mobile design. So that's the first suggestion for how we can rethink the way that the spectrum is used. The second one is a little more radical, if you thought that one wasn't radical. So basically, nationalize the cellular radio networks into one regulated network. Basically amalgamate all the spectrum in one country into one regulated network. So I'm not kidding, and I'll explain why. So radio relies on a shared limited resource, the radio spectrum, and that's a given. And the industries that rely on such resources, and water and power are the two most obvious ones, they need to be very carefully planned. You can't just let the market do whatever it wants. And I first had this idea when I saw a documentary about a year ago about the history of the electricity industry in the UK. And way back in the 1920s, there was great competition, great choice. You could have any frequency you wanted, any voltage, DC or AC, you name it. And it was delivered to you by a dedicated, power station that you could, it was probably nearby because obviously the cables had to run direct to your house. And that was the ultimate in competition, deregulation, free market. The trouble is, the continuity of supply, the coverage, it was pretty patchy. And of course, you couldn't roam. You couldn't take your device that was working in one house on one voltage or whatever and move it to another. So that's what we had. And then some rare visionary in government, they do come along now and again, proposed to create a national grid, join up all the power stations. Now, of course, to do that, you have to agree on the voltage and the frequency and the phase, for that matter. And it was this whole exercise that led to the understanding of transmission line theory, the fact that you could get standing waves on these cables that were hundreds of miles long at 50 hertz. So this was quite a challenge, and the industry was dead against it. They said, well, this is anti-competitive. How can you do this to us? The government went ahead and did what it did, and then about 30 years later, they went one stage further, and they nationalized all the generating companies as well. And they created the Central Electricity Generating Board. And at that point, the scale of the industry was such that the costs went way down, and the coverage and the performance of the industry went way up because you had redundancy in the system. And if one power station went down or whatever, it didn't matter because you had another one covering the grid. So that's what's happened with power now. Who would want to roll the clock back and say, no, we need more competition? Now, there is competition in today's electricity industry at the service delivery level. So I can buy my electricity from a number of companies who all have their own prices and whatever. I know it's coming down the same wires. So there's a wholesale market in the UK. And then the individual operating companies are doing all the back office stuff, the billing and all the rest of it, the meter reading. That's where the competition is right now. But the actual generation of the primary resource is very much controlled, regulated by the government. It's not necessarily owned by the government, but it's regulated by the government. Examples of fragmented infrastructure. Japan is a good example. The west of the country, which was influenced by Europe, is running on 50 hertz, and the east is running on 60 hertz. Same voltage, 100, which is of course different from any other country. Gives us nightmares when we're creating multi-voltage power supplies, but whatever. The problem with that is that has had a direct impact on their ability to deal with the recent tsunami, because they lost the generating capacity in the east of the country, and there was excess capacity in the west that they couldn't use. So that's an example. Australia, 3 different gauges of railway. So they're the only country in the world that had to come up with bogie switching technology. So they take the top of the train off one bogie and put it onto another so they can carry on. Edinburgh, which is where I come from, used to have 2 sets of railway lines coming from London, 2 different companies. Can you imagine doing that now? We can't even get a tram built in Edinburgh. 1 tram line from the airport to the city centre. And they built 2 full sets of tracks all the way from London to Edinburgh and put hotels at each end of the Princes Street. So fragmented technology at that level doesn't really do you any favors. So thinking back to cellular now, clearly cellular's come a long way. It's no longer considered a luxury. It's now considered an essential service. And you see the impact of that in places like Germany, where the government's said the LTE rollout 800 megahertz is going to go to rural communities first. You know, so clearly it's no longer considered a luxury competitive just for those who happen to live in the cities. But the history of radio has led to this situation where we have this fragmented spectrum within countries, within operators, within, you know, across countries. And this is the result of policy. In many countries, the regulator requires at least 2, maybe 3, maybe 4. In the UK, 5 operators competing for the same spectrum. And maybe this was the right way to do it in the 3rd generation. I still think that was a big mess, that whole spectrum auction, but whatever. But what if the government actually started thinking more holistically about the problem and said, well, we've got this limited resource, we now need it in bigger chunks than we ever did before. Why don't we start to think about this in a way that is more efficient for everybody and stop selling off this asset as if it were something that could be you know, sold to the highest bidder. So what might it look like? Well, it's certainly happening. IOTA in Russia is already kind of looking at this. But we have had what you might call anti-competitive situations in the past. And I think Stephen Temple could speak to this more than myself. But it's pretty clear that it wasn't competition that created the phenomenon we know of as GSM. It was actually collaboration. It was broad, long-term thinking by multiple governments, looked at this and said, let's do something collaborative. And they did, and it was fantastically successful. And then you see, well, what did the US do? Well, they did quite the opposite. At the same point in time, or slightly after Europe, they did the opposite. They said, let's just, you know, we've got our spectrum, we know where it is, but let's not mandate the technology. Let's let the market decide. And what did they get? Well, I think history has shown that that was a very damaging decision by the government, because they ended up pursuing 5 technologies. Only 2 of them have survived, and those 2 do not speak to each other in any meaningful way. You have to effectively have 2 totally independent radio stacks, multi-format radio. And yet the government at the time, you know, just after the spectrum auctions, was thinking, wow, isn't this wonderful? And I can't find the original quote, but I was on the White House website one day and I came across this quote from someone in the government praising the FCC. Look, you know, they generate money, the rest of government spends it. You know, why can't all government departments generate money? And basically they're just taxing, you know, they're taxing the industry for selling off a public asset, which is not necessarily the smartest thing to do. So wireless has a very long time span, and you've got to be very careful how you manage that whole infrastructure. And I think that the regulators are stuck in the past in terms of insisting on continued competition and fragmentation. And we really need to think about this differently. So network sharing is becoming more of a reality. The industry is figuring it out for itself rather than having to be forced on. And as I mentioned a minute ago, IOTA is probably the best example of what might happen in the future. They've teamed up with 4 of their competitors in Russia, and they're trying to build one LTE network. They're pooling their spectrum. So they're creating scale, they're simplifying the devices, they're providing a single network. They've got more money to spend as a group to put up one set of antennas in one area, covering a broader frequency band, and basically providing a service, I think, that is going to be superior to anything that any one of them could have done. And as we know, typically within countries, you're not allowed to roam within your own country. That's another regulatory restriction. So, you know, you go abroad, you actually get a better performance than the local people do. That's pure politics. That's not, you know. But national roaming doesn't solve the problem. It helps. a national network means you then don't have the overheads in the actual infrastructure. Well, somebody you might say they're communists, but that's just the way it is. Maybe they're just smarter than us. So it should be obvious that if we pooled all these resources, things would get better. And if we regulated this operator in the same way that we regulate the power industry, we set expectations on what they can do, performance, etc., maximum wholesale prices, we could end up with something that really is quite attractive. And then the rest of us can get on, knowing that there's this ubiquitous network out there, the rest of us can get on and deal with the real challenges, which is designing the devices, the services, optimizing the cost out of the rest of the infrastructure, the mobile part of the infrastructure. So, just drawing to a close here, I think we've reached an inflection point with spectrum, and we need to think more centrally. And I don't know, between countries, it's probably going to be a long time before we get agreement at the ITU level. But within a country, it seems to be well within the capabilities of a government to make decisions on how they manage those assets. And we shouldn't be worried about that, because regulation typically is a retrospective thing. You start off in a free-for-all, the old land grabs of the past. There was no regulation. But now land is heavily regulated with planning permission, all the rest of it. Spectrum kind of has gone the same way. It's gone through a period of kind of like who cares to one of being regulated to this competitive environment we're in right now. But there are other ways of looking at it. So just before I close here, I don't know how many of you have seen this before, but I thought I'd have a little competition. This is what happens when you have greenfield planning. And I've got a little giveaway here. I have a habit of giving away whiskey in my talks. And I've got a little bottle of liquid to enjoy here, which is my LTE whiskey. So anyone who's not seen this slide before, can anyone tell me what that is and where it is? This is an example of greenfield planning. This is what happens when you have a clean sheet and no constraints. Oh, you've seen it before, though. Yeah. So who's not seen this? Any idea what this is? You have seen it? You haven't seen it? Okay. Well, if I tell you it's an airport, does that help? Okay. Right. Anyone any idea which airport this is? Very good. Okay, you win the first bottle of liquid to enjoy if you want to pop up. So this is I think this one's Speyside. I'm not entirely sure what it is, but anyway, there you go. There's a little joke in the back. Right, so this is what happens when you have lots of space. This airport, I believe, is about 50 square miles. And you can see it has runways in every direction. This is an example of diversity in runway design. They have no problem. So they were able to do this. So for my next and final giveaway, can anyone tell me where this is? Well, I've already said, I can't give it away. Rats. I didn't animate this one. Anyway, this is Heathrow Airport. And it's basically probably one of the most inefficient, messy pieces of engineering on the planet. You've got first generation there, second generation there, third generation there, fourth there, and then they just opened the fifth terminal on the left here. And if you're in any one of these terminals, especially the new one, Terminal 5, it's great. You've got to travel between them. It's a nightmare. And you really see that the back end of Heathrow is not a pretty sight. This is the result of years of just ongoing evolution without any real control. And it's created an infrastructure that really is not good compared to what you can do in Denver. So these are the two extremes. The greenfield, let's just get it right, and then the how on earth do we manage this asset that's, I don't know how old it is now, but it's clearly long past its point that anyone could say this thing was a plan. So getting back to cellular, what is it that we need to do now in cellular? We cannot just do a Denver airport. It would be great if we could. And what we would do, if we could do it, is we'd just throw everything away and we'd put LTE out there and everyone would be happy. And while we're at it, we'd fix all the frequency bands, we'd have one big frequency band. And that would be fantastic. I don't think anyone would disagree with that as the best answer. But the investment in cellular is so huge that we're somewhere between Denver Airport and Heathrow Airport. We've got a limited range of things we can do. And one of the things I think we can do within the constraints, the practical constraints of where we're at, is that we can aggregate national spectrum, make that a priority of governments, and at least solve the problem in your own country. Give people access to all the spectrum, simplify the terminal requirements, get better coverage. You no longer have this situation where you go and buy a house and you have to look and see which network works and which doesn't. There would be a whole lot of benefits that could come from that. There would obviously be a lot of legal and financial issues about how you move that asset that's currently privately owned and was sold off back into public or into public ownership in some way. But I think it really is something that is worthy of debate, and I think that Russia, of all countries, may be showing us the way there. So that's my two radical ideas, and thanks for listening.
Thank you very much, Moray. You might like to go back to if you remember, the Spectrum Management Advisory Group that Stephen Temple and I were members of.
All right.
In the minutes, you will find, I think, a note to government saying one spectrum shared between all the operators for 3G. But unfortunately, ministers didn't quite understand what we were saying or why we were saying it. And we got what we got, which you've described.
Yeah.
Have we got any questions? Because we need to move on fairly quickly.
Yeah.
So that was quite interesting. I just wondered, you mentioned Jota Skartel in Russia as being a sort of a thought leader in this whole process. How do you see competition amongst the big four that you mentioned in a very competitive environment such as Moscow using Jota spectrum?
The finer details, I don't know, but the question in general is a good one to ask. I mean, the question is, do you necessarily want competition? I mean, if it is properly regulated, I think you would like to think you could get the best of everything. One set of brains being applied to one problem. You could argue that there may be some things that wouldn't happen as a result of that. But I'm thinking back to some of the other industries which have been effectively regulated at the national level for reasons that go beyond the competitive aspects between companies. So yes, for the individual companies, I'm sure there'll probably be arguments for why they would want to hold on to what they've got because they think they can do a better job than the next guy. But is that necessarily the right answer for the entire industry? And that's the question. So I don't know how they would deal with it. And of course, in Russia, there's all kinds of other political and maybe not so political aspects that may be related to even this deal. I don't know. But I think as a model for what could be done, I think it's a very interesting one and one that should be watched.
Okay, I think we probably ought to move on because
okay.
Interesting ideas.
Yeah, well, there's a debate later on in the afternoon about this whole thing,
exactly.
So I expect that will...
opportunity to...
Yes.
We don't take all of Helen's opportunities to have questions and discussion later.